Hello, everyone. Now we want to continue designing our detention basins. In the previous lecture, we learned how to understand the need for a detention basin, why we want to have a detention basin in our watershed, where to put it. Also, um, the schematic of a detention basin, which usually has two separate storages, one minor storage responsible for frequent storm and another one called major storage, which is responsible for flood control and also extreme events. So in this particular lecture, we want to come up with the dimensions of the major storage. And let's see how to do it. This is what we have so far for my study area. It is a minor storage. We have a side orifice at the bottom, which is responsible for the water release for the water quality capture volume, and another orifice, which this one together with the bottom orifice are responsible for releasing water for the 2-year event. And we learned how to iteratively run swim to come up with the dimensions of the orifices. And we learned that at the 2-year event, in a situation that we have both orifices, the maximum water depth is around 2.22 feet, meaning that we can basically trim our minor basin at this point and then learn how to extend it for including the major storage. And this is what we came up for the hydrographs. We had a little pre-developed peak flow of around 4 CFS. Urbanization made it, as you can see, like 8 times higher. And now with the detention basin, we can match the peak flow to the pre-development condition, but the volume of water, as you can see, is virtually the same as the uncontrolled condition. Because again, detention basin cannot dissipate any water. It doesn't support infiltration or evaporation in its normal design. So this is what we have, and now we want to continue. Just to remind you of a schematic, we are now done with this minor storage. Now we want to extend it abruptly to have additional storage for a 10-year and also a 100-year event. So the two-stage design, again, we expect this part be underwater most of the time, frequently, and that helps with the people who want to do the maintenance and inspection. And also we don't expect the major storage be full of water in a normal situation. That is why we call it extreme events. So as you can see, orifice number 1 controls the release of WQCV, 1 and 2 together for the 2-year, 1, 2, 3 together for the 10-year, and all 4 for the 100-year. Just pay attention that number 4 is a Weir. That is because we want to have a flood control and overtop control. If you get anything larger than that, that helps and acts like an emergency exit and bypasses the water, so it can go. We don't hold more than what we can handle in the basin, and that depending on the local manual, you need to have a drawdown between 24 to 96. In this example, we used 40 hours. But again, a prismatic basin is mostly presented in this lecture for simplicity. In reality, you might have any forms and any shapes for your basins, usually irregular shapes. And for those of you who are doing land development projects, you know that geometric software like MicroStation and Civil 3D can easily provide the surface to depth areas for different shapes. The focus of this lecture is not teaching you how to learn how to work with microstations or Civil 3D. That's why we're presenting a prismatic basin. But as long as you have the relationship between area and surface, the surface area and depth, that's all you need for swim. You can extract the surface area and depth relationships from software like Civil 3D and just plug it in to your storage curve in Swim, and then find the right dimension, find the right depth. That's all you need to do. And as you can see, we typically have a riser, a weir on top, of course a trash hood. We want to avoid a situation that trash can clog it, and different orifices. Here I'm showing one orifice and one weir, but then we typically have one, two, three orifices here and one weir, and of course an embankment to hold the water, and then this pipe to drain the system, and some riprap at the end to control the erosion. And that's a typical design. And a figure of the riser is this one, a rectangular weir. There is definitely one at the end, but it's kind of blocked by trash. You can't see it. And the weir, and this is the trash structure, so we don't allow large debris going and clog the system. And that's the embankment that you can see, so the water is held here. Okay, and last reminder, for the prismatic we use a length to width ratio of 2 to 1, side slope of 4 to 1 is pretty typical, and WQCV depth, that's really up to you, usually less than 2 feet. In this example we use 1.5. And just some basic geometric equations. These two, L2 and L4 equation, that helps you to understand what is your dimension at any depth, given the base dimensions that you have. For L1 and L3, you can, for example, for the WQCV, you can plug in 1.5 for H1, and it gives you the dimensions at the upper side of the prism. And you can do this also for 6 feet and everything. That's our key equations to come up with dimensions. And then the surface area at any depth is just we multiply L2 by L4. And also for WQCV, to solve it, WQCV volume comes from manuals. It's just you follow some charts and some graphs for rainfall, and some tables for imperviousness. You have this. And for a given depth, like H1 equal to 1.5, you can solve for L3. So that's how to come up for the dimensions for the WQCV. Now we want to continue. So first thing first, we learned that our water at the 2-year event is going to have a depth of 2.22 feet. So something around here. We don't need the extra storage for sure. We need to trim this. So at the 2.22, we just put the right number. So we introduce additional data points, so we can turn. We can turn left here, and then we can turn right here. Just plug in the equations that I showed in the previous slide. We can solve for L2 and L4 and multiply, so it gives me this number on 20,000 square feet for the area at the point that I want to trim. And just slightly above that, we can abruptly enlarge the dimensions. Why not exactly at 2.2? Because we want to, like here at this number about 2.2, we want to turn left. We avoid flat surfaces and flat slopes in drainage engineering at any situation. You won't see anything. Everything should have a slope on side, because we want to promote the drainage part. So just slightly above that, at 2.3 feet, we can like suddenly double the dimensions. And that is helping us to be able to come up with a surface that is significantly larger. And finally, having this new base, like this is base that is larger, then we can find our dimensions for the maximum depth of 6 feet. So this is what you end up having. Do you see, like if I was expanding my minor storage, it was not large enough at 6 feet. But now I'm turning left here, I'm turning right here. So I know what's my dimension at 2.22, a little bit, just round it up like 2.3, 2.4. These are all fine. Now I can, it really depends on your scale of the project. Usually doubling the size can give you what you need, but you can multiply by 3 or 4. This is all depend on the site suitability, like how much space you have to put a basin like this. If you are multiplying by the area by 4, it means that each dimension that you have, you're doubling it. But if you're doubling the actual area, then you're not really, as you can see in this figure, we're not really doubling each dimension. It is, of course, smaller compared to a case that we are doubling each dimension, which is resulting to multiplying the area by 4. So in this example, I just doubled the area, and this is my, the side view of it. And then now I have my numbers for depth equal to 2.3. So with those dimensions, I can again plug it in into the general equations for L sub 2 and L sub 4, and then solve. uh, Basically, if I go to previous slide right here, just do, assuming now I have new L1 and L3, because at depth of 2.3, I'm using a new surface as my base. So assuming I have new L1 and L3, now I can solve for L2 and L4 for h equal to 6 feet. And that's the resulting figure. So yeah, in this example, we plug all these numbers in SWM and we update our storage curve. Before doing this, I was calling it my minor curve, but now I call it combined. And now step 2 is just running the model 10-year storm with what you have. And in this example, it is giving me these numbers. Just as a reminder, my target CFS for 10 year was 7.34. So let me show you what I end up having in this example. So here I have my detention basin right here. It's draining with orifice 1 and orifice 2, the dimensions that I solved for in the previous lecture, and make sure I'm selecting the right time series. Yes, that's 10-year. And this is orifice 1 and 2, and then draining to this node, and after that to the outfall. So if I run, solves. So basically, I want to see what's the depth in the storage, what's the peak flow at the node. So depth in the storage, you can plot it. It is about 3.2, but there are easier ways to find the actual exact maximum which you need. So that's through your static report. You can have depth, peak, and um, the depth is 0.88, and also for the node, make sure you select the total inflow. That's 7 CFS, but again, the exact number you can find it from the statics. That's 6.99. So numbers like that, but there are some you know some errors in solving the continuity equation. So you might run the stream twice, but then each time the numbers are slightly different. That's because of the computational algorithms and numerical methods. So yeah, like in this example, I am getting about 6.96 or like 7-ish CFS and the maximum depth of 3.2. So in this example, just to make sure I'm showing you the right variable, That's 3.2. Also in the statistics. Oh, you need to pick the right. Yes, so that's SU storage unit number 1, depth, and peak number, that's 3.2. So previous time I showed for a different node in the system, 3.2 is the right number as I'm listing it here. So this is not okay. We know that we need to match. If we exceed the target, that is dangerous, that is causing flooding. If we are smaller than that significantly, then that means that we are over designing. So we want to be as close as possible to the target. So basically just leave it as the pre-development situation and don't change it any further. So for that purpose, we might need to add orifices, and we do need to do it here. So for the orifice, we, just similar to the previous lecture, we pick a side orifice that is a rectangular shape. We put it at the bottom, but here our bottom is just the top of where we ended up for the 2-year storm. So 2.22 was my maximum depth for the 2-year storm. So now I use this as the offset for my new orifice, the orifice that is responsible for the 10-year. Then we size it iteratively, and then, this is a very iterative process, but a quarter of a foot is somewhere to start for both width and height. So let me show you what I have. So that's where I left off for the 2 orifices. Basically, we just need to um, add another one, but again, we want to make sure that we can see them. So this is just a visualization. We're not shaping the orifice like this. It just helps us to don't mix them up. And this is not a distributed model. Everything is just a visualization, and we put the numbers and dimensions manually. So you select from here, you might put it somewhere like this, and just double click, so then they're not on top of each other, so you can easily select and see what's going on. And so I have the dimensions already inserted to save time. This is my orifice number 3. Let me show you what we have here. This is a side orifice, not bottom, rectangular and closed shape. So this is like where you can start, quarter foot, and this is the offset. The offset is 2.22. That's the maximum depth without having this orifice under a 2-year storm. And we leave the 0.65 discharge coefficient as is, and we run, save and run. So now we again check numbers. Now for the peak, we're about 12 and some change, and for the depth we are about 6. Continue our notes. Yeah, so we want to match to 7.34. So that's what I'm going to do in this new orifice. Then I did these iterations and learned that 0.35 is helping me to get to what I want. That is not the right number. I need to make sure I am running the model with the right rainfall. So let's do it again. So yes, now we're getting near 7.3-ish that we wanted. We can again check the exact number. That's gonna be my uh, outlet node just below the orifices, and total inflow we are doing peak. We can leave the rest as is. Then that's 7.344. Now we are exactly matching the target. You don't have to do this exactly. uh, Anything a threshold of a tenth of a square tenth of a cfs is fine. But yeah, in this example, as you can see, I'm using these dimensions. It's giving me 7.3 for cfs, and for maximum depth is about 3.17 feet. And that's the result. That is the if I plot all these hydrograph in one shape, then I'm matching the pre-development conditions, but of course a lot larger volume. And just to show you the quick ways, if you want to like show all these in one figure, instead of plotting the figure, you can get the actual underlying data. So you have total inflow at this point. You can change this to date, doesn't really matter. And this is giving you the data. So you select, and then you copy to clipboard. So you can copy to clipboard, and then you can paste in Excel. So then you have it. Then you basically paste other things, and then you can um, just use Excel functions to draw whatever you want. As you can see, then that's an Excel exercise. So yeah, now we can minimize this, and that is what I needed from this run. Now I did this iteration, and then I know the right sizes, so I can match the pre-development peak, and I know what is my depth. That is very important because next thing happens just right above this. So we are doing this sequentially, basically. So yeah, the next step is now doing for the 100-year. The only difference this time is that now we're dealing with a weir, not an orifice, because this is going to be also our emergency drainage mechanism. So here we have a situation, we have 3 weirs in it, and then I'm going to run and see what I'm gonna get for the 100-year. This is my model. I change this to 100-year, and I run. So I want to see if I can match my target for the 100-year or not. Plot is the fastest way for me personally, because I can see what's going on, things make sense or not. And that's about like 12.3-ish CFS, which is not what I want. I want to be around 31.6. Again, this is smaller, but this is showing that I am not matching. I am over designing. I can modify my dimensions um, just to be somewhere that I can match um, the pre-development conditions. Plus, another thing to pay attention here for the final weir is that I want to make sure that when I add my weir, the water is not overflowing my basin. So that's another criteria. We have to, in this case, we have to add a weir because we want to match the pre-dev. Also, we want to make sure we're not exceeding the 6 feet. So transverse weir is typical rectangular shape. Just pay attention that here we're dealing with something that has much higher discharge coefficient. Of course, a weir can convey water way better than an orifice. And we just put it right above the 10-year max. And in previous slide I showed you I have 3.17 in my example. This is also giving me what's the height of my weir. I have at 6 feet total, 3.17 is the offset, then the remaining 2.83 is what I have for the height. And then I size it iteratively. So in my example, this is what I have. Then I'm going to show you. I usually copy these as new files so I don't lose things if I mess things, if I mess something up. Then this is my everything. I don't have the backdrop, but uh, yeah, now I added this weir thing, basically similar to the orifice. This is a weir. And again, the reason that I'm doing this extra vertex right here is because I don't want to put them on top of each other. That helps me to understand quickly how many of them I have and how to select them. But yeah, what I have here is just stuff that I discussed. It's transverse. You have these options, but this is the most popular form of veer. The height is what I have available. I have 6 feet total. Then in the 10-year model, I showed what's the maximum depth, and I'm using that as my offset, and this is giving me 2.83 available. This is what I need to solve iteratively. We can put different numbers. That's what I have after doing the iterations. And that's the inlet offset. That came from running the 10-year model. This is 3.3. Use this as the typical number for a veer, transverse veer, and don't worry about everything else. So yeah, let's run this. So if I run, make sure I have the right rainfall and save and run. So now here for the Q, I have 32-ish. And for the storage, I have 5.4-ish, which is a good news. 6 feet is my maximum. Usually manuals require having a freeboard of 1/2 foot to 1 foot. 1 foot is pretty typical, but then you can basically add that. You can extend the dimensions for another 1/2 foot so you have that freeboard if needed. That's really something that does not involve the hydraulic calculations. So just something to remember. So we're good for the water depth in this, and also yes, so I'm matching the 31.2 like I'm matching what I had with, with some differences around 10th of a foot, or anything less than half a CFS is fine, and maximum depth, which is good. But I can show you what happens if I use different dimensions. Like for the veer, if I don't use this and use a size of a 1/4 of a foot just as an initial point where I started, then I run, but I might see some things that I don't like to see. Like this is basically leaving the water, leaving the basin, and that's like kind of shaved at that point because the model is unable to show what happens when water leaves the system. We didn't add enough system elements, like if what happens if this flooding happened. We would definitely want a situation that water is all the time below 5.5, or in some guidelines they require to have below 5. I mean, having a 1 foot or half a foot of freeboard. So then that's something to consider. Also, at the same time, you need to pay attention to what's happening in terms of your cube. So in this case, of course, Q is uh, much lower than target because the weir is not large enough. The weir is holding too much water, so it's controlling the discharge, which is a good thing for flooding of downstream, but not flooding of the actual basin itself. The basin is flooded; it leaves the water. And yeah, you can test other things, but just to show you some scenarios that can happen if you have like 5 for the length and run. So now we have a weir that is oversized, it's too big. So of course we don't flood the basin. Yes, it's 5 feet now. We have 1 foot extra empty, but then now we need to worry about the flooding of downstream, folks, in terms of total inflow. Now we have 50 CFS leaving the system, which is not what we wanted. We wanted to be around 31. So 160 post-development has to match to 31 HCFS, so we can make sure that this land development project is not causing additional discharge to people living in the downstream areas. So that is the final step. Now you can celebrate finalizing your first detention basin design. Very popular BMP for stormwater management and flood control. Just to go over what we have so far, we have 3 orifices and 1 weir. The bottom one for WQCV, one for the 2 years event, and these two together are draining the minor basin. Right, uh, we had at 2.22 feet the maximum depth of water for the 2 year event. Just a little bit above that at 2.3, we are expanding this, so that's like the kind of mild slope between the I know the sizes that we have the abruption, because again we want to avoid a flat side. That's helpful for flooding and flood management. And now we have our third orifice like this, just right above the minor storage. And then on top of everything, we have the weir. We are also showing what we expect for the maximum water depth. Of course, this is for the 100-year event, which is the most significant that we address. 100-year event in stormwater management is usually the goal. We don't really design things for 500-year events and things like that. For most culvert and pipe and conduit design and flood management, 100-year is our target. And we showed that 3.17 is the maximum depth of water under a 10-year event. We just use this number as the offset of the weir. And all other dimensions that you can see, 6 feet for the maximum. So now we have about half a foot of freeboard in this example, and all dimensions of orifices that we solve iteratively. And this is a summary of what we have: 3 orifices, 1 weir, height, width, invert offset, that is basically coming from solving the model for the previous condition. Like 10-year event gave us insight what's going on for the maximum depth. Then we use that as the offset for the 100-year. And discharge coefficient, pay attention that a weir has a significantly higher coefficient compared to an orifice. And summary, we first part for the designing the WQCV or FSV did not link it to the actual model. Again, because WQCV is a hypothetical rainfall depth, it's not an actual data. It comes from following the manual for some imperviousness assumptions, some isopovial maps for rainfall depth, and gives you a volume. So we just did not link it. It's a lot easier to do it that way, because if you do link it to your actual model with actual design storms, then you need to kind of back calculate things, and it's unnecessary. And so we did this sequentially, as I explained. The maximum water depth, we like for 10-year storm, we did this. And when I wanted to add the Weir for 100-year, then I used that as the invert offset for the 100-year of the next design storm, next larger design storm. That's 100-year in the example I mentioned. And there is equations for the orifice and weir. In the previous lecture, I explained some reminders, but I'm not really using them because we do need to do the iterations eventually. It is always easier just to do the iterations. If when you see you have too much peak discharge, you basically make your orifice larger, and vice versa. So just so you are aware, for the initial guess, you can use those equations if you want. And lastly, very important to note that detention basin can effectively mitigate the peak runoff rate, but has no effect on the runoff volume. And that is making it interesting to introduce the green infrastructure later, because they are also able to address the volume by promoting infiltration and evapotranspiration. And that's the reference that I used for this presentation. Thank you very much for your time.